In this video, we're going to simplify radical expressions containing variables. Now, to be fully simplified, these expressions still have to meet the 4 criteria of a simplified radical expression. The radicand can't be negative. It can't be a fraction. A radical can't be in the denominator of a fraction. And if we're simplifying a square root, the radicand can't be divisible by any perfect square. And if we're simplifying a cube root, the radicand can't be divisible by any perfect cube. So let's look at the example over here on the left. We want to simplify the square root of z to the 13th power. First things first, we need to find the biggest perfect square that will evenly divide z to the 13th. So here's a list of perfect squares for the z variable. Z squared is a perfect square because it's z times z. Z to the 4th is a perfect square because it's z squared times z squared. Z to the 6th is a perfect square because it's z to the 3rd times z to the 3rd, and so on. Notice that all of these variable perfect squares, the exponent on them is a multiple of 2. 2, 4, 6, 8, 10, 12. And we'll see that pattern for all variable expressions. If the exponent on a variable is even, or if it's divisible by 2, then it's a perfect square variable expression. So now the question is, what's the biggest perfect square that will evenly divide z to the 13th? The biggest perfect square z expression that will evenly divide z to the 13th is z to the 12th. Notice if we went up to the next z perfect square, it would be z to the 14th. Well, that's too many z's to evenly divide z to the 13th. So now let's write the square root of z to the 13th as the square root of z to the 12th times z, because z to the 12th times z is still z to the 13th. And by the multiplication property of radicals, the square root of z to the 12th times z is the square root of z to the 12th times the square root of z. Now simplify the square root of z to the 12th. The square root of z to the 12th is z to the 6th, because z to the 6th times z to the 6th is z to the 12th. So that gives us z to the 6th times the square root of z. Now we have to look at the square root of z and ask ourselves, is that a fully simplified radical expression? For this expression to not be fully simplified, the exponent on z would have to be 2 or greater, because this is a square root. The exponent here is 1, so there's not a perfect square z expression that will evenly divide z. So that means the square root of z is fully simplified. And our final simplification is z to the 6th times the square root of z. And that's the fully simplified form of the square root of z to the 13th. Now let's look at the example over here on the right. Let's simplify the cube root of x to the 5th. Let's start by identifying perfect cubes that will evenly divide x to the 5th. X to the 3rd is a perfect cube because it's x times x times x. X to the 6th is a perfect cube because it's x squared times x squared times x squared. X to the 9th is a perfect cube because it is x to the 3rd times x to the 3rd times x to the 3rd, and so on and so forth. Now the question is, which one of these is the biggest perfect cube that will evenly divide x to the 5th? X to the 9th is too big because there's too many x's there to be able to divide only x to the 5th. Same thing with x to the 6th. Too many x's there to evenly divide x to the 5th. However, x to the 3rd will evenly divide x to the 5th. So when we're choosing which variable expression will evenly divide our radicand, we're always going to choose the one with the exponent that is the closest to our exponent in the radicand without going over. So x to the 3rd is the biggest perfect cube that will evenly divide x to the 5th. So let's rewrite x to the 5th as x to the 3rd times x squared. Now, using the multiplication property of radicals, we can rewrite the cube root of x to the 3rd times x squared as the cube root of x to the 3rd times the cube root of x squared. Now let's simplify the cube root of x to the 3rd. The cube root of x to the 3rd is x, because x times x times x gives us x to the 3rd. So now we have x times the cube root of x squared. Now we have to ask ourselves the question, is the cube root of x squared fully simplified? And an easy way to tell that, and I alluded to this in the previous example over here on the left, the easy way to tell that a radical expression containing a variable is fully simplified is to look at the index of the radical and the exponent in the radicand. In this example, the index is 3 and the exponent of the radicand is 2. When the exponent of the radicand is less than the index, then that expression is a fully simplified radical expression. Notice over on the left, the index, because we were working with square roots, is a 2, and the exponent on the z in the radicand is a 1. 1 is less than 2, which means that the square root of z is a fully simplified expression as well.